for thanking me and us for coming from so far. I came from 5 minutes away on a bike where I live to my office 2 minutes north of here, and then I walked here. I knocked on my boss's door and said, I'm going to go give this talk, and she says, oh, have a fun time. So thank you for inviting me to this, the first Dorrance lecture series as the first speaker. I'm really honored to be here and to be able to talk with both the scholars and the community that's here. This is really exciting for me. I absolutely love talking about what I do, and I'm very lucky because I work on the coolest thing. I work on astronomy. I'm a black hole hunter. I'm a galaxy finder, and I'm going to talk to you about something that is very important, which is how can we study and understand and think about astronomy as human beings, like we are these tiny humans in the face of the vast, insane universe. And so that's what I'm going to try and bridge today. And I'll tell you a little bit what I do throughout. And so I'll hopefully get you excited about the thing that I do, which is a super awesome thing in conjunction with NASA. And then at the end, if you have questions, you should ask me. I love talking about this, but I also love talking about the way that I got to my job. And so if you find me in a hallway or if we are having some snacks later on or something like that, please ask me about the weird journey that I took to get to where I am right now. So this talk starts with this. So who, especially if you're in the front, what is this? People in the community who know this and are being very smug, just be quiet for a second. What is this thing right here, especially in the first couple rows? It's a satellite of sorts. I will give you a hint. It's the Blank Space Telescope. It rhymes with rubble. I heard someone say it. It's the Hubble Space Telescope. This is NASA's most important space telescope. The Hubble Space Telescope, it was launched in 1990, which means it's probably older than some of the people in this audience, which is insane. It is a telescope that's been up for almost 30 years, orbiting our planet, which is why you see our planet below. And it is this incredible eye that NASA built and put up there that has been an amazing boon for us astronomers. It has opened up a window to the universe, a high-resolution imaging window to the universe that has changed astronomy entirely. And for many people, for us astronomers, our interaction with Hubble is through its incredible data, deep data sets on a variety of topics. For many people, the way that they know about Hubble is through the images, these incredibly beautiful images that, like, for us astronomers, give a huge amount of information about what's going on. So what you're seeing here is you're seeing baby stars being born in a little stellar nursery. And Hubble took these images. This is star birth here, right? This is also, someone might look at this and go, I think I have that on my yoga pants. Like, this is a very pretty image that is, and like, that's an important aspect of what we do as astronomers, is produce pretty images. Because you would put this on there because this is gorgeous, the colors and the shapes. And like, for an astronomer, we might look at this in a very cold way, but I want to argue through this talk, and spoiler alert, this is kind of my argument, that we should be viewing astronomy through an aesthetic sense. That we should view astronomy with our heart, not just our rational cold brain, because otherwise we're losing a huge aspect of it. Hubble also took images. This is a zoom in of like, baby stars are being born in these columns. You can see the light that's coming from other stars blowing the gas away. But this is essentially a stellar nursery, what I said. Astronomers can look at this and tell you about how stars are born. All right. Also, how stars die. This is the remnants of an exploded star. This is what happens when a star blows up in a big gas cloud. It just blows a big hole in the middle, right? So this is another Hubble image, or this incredible Hubble image of a galaxy, a spiral galaxy, and you can just see all of this stuff. So Hubble was and is this amazing thing that for maybe the first time, really, it took astronomy and put it into the eyes of the populace. And there were other astronomy pictures, and we had spacecraft that went to other planets and took these pictures. But I think that Hubble did it in a way that had never been done before. And I think that it's underappreciated how important that was, both as a thing to inspire. This thing was launched when I was young, and I looked at these images and felt something stir inside of me that drove me to astronomy. And I think that that is something that we need to remember is vital for this field and for all of astronomy and for the sciences, is how we present science to the public. Because sometimes as a scientist you can think about, I'm only doing science for myself or for my colleagues or for the people who read my papers. But that is not how you should view science. You should view science as a thing that you are doing as a gift and as a product for the world. You're pushing science forward even little ways. And Hubble pushed it forward in incredible ways. The amount of information held in this and the amount of beauty that, is like, you can't count it. And the reason that I'm here at the University of Arizona is because Hubble's 30 years old, and NASA, for the last 20 to 30 years since it launched, has been planning a next generation of space telescope, the next generation. And Hubble has been supplemented with a lot of other telescopes at other wavelengths in space that are doing a really amazing job. But they wanted to make a next generation space telescope that was bigger and more robust and answered bigger questions. And so here is a, here's like what it looks, it's about the size of a school bus, Hubble. Here's a person next to its mirror, so the mirror would just kind of sit right here. I'm about to show you an image of the telescope that I work on, and I want to prompt you because people don't need to be prompted with this. When a telescope is bigger, it is better. So the bigger this is, the more of an ooh I want you to give me, okay? So are you ready? So this is the telescope I'm working on. Ooh, oh, yeah, wow, it's incredible. This is the James Webb Space Telescope. The mirror would barely fit in this room, right? It's 6.5 meters across, like 25 to 30 feet across. It's enormous. The telescope is the size of a tennis court. The telescope itself would barely fit in this room altogether. Hubble could just park right here. James Webb would just barely fit in this room. The mirror is gold-plated 18 hexagonal mirror segments sitting on this beautiful sun shield like a flower sitting on a petal in some water. This is a kind of zoom-in CGI of it where you can see, so for people who are unfamiliar with how telescopes work, the light comes in from space, bounces off this primary mirror, bounces off a secondary mirror right there, and into this tiny little hole here where it goes to the instruments that are back here. And so those instruments we'll talk about in a second, and I'll talk about why there's this big sun shield as well, but that's the pathway of the light. It's not like a telescope you might know where it's got a big tube like Hubble. It's open air, so that is, because it's so big, it would be very hard to fit a tube in there. In fact, the way that it's going to launch into space is folded up in a rocket. I went and gave a talk on this at an origami art exhibit at the Tucson Botanical Gardens last year, but it has this beautiful unfolding process once it gets up to space, which is very beautiful, but also terrifying as a person who hopes that it all works when it goes to space. When it goes to space, it's not going to do what Hubble does, where Hubble just orbits our planet. It's actually going to go 1,000,000 miles away to a spot beautifully labeled L2 for Lagrange point 2. And what that is, to do a little dance for you guys, again, this is a Humanities conference, so I'm going to do a little dance for you guys. Imagine my head is the sun. Imagine that this is the Earth. L2 is a spot that stays on the other side of the Earth from the sun. Okay? And it's actually going to kind of do this a little bit. It's going to orbit around that spot. But it just essentially keeps the Earth between it and the sun. And this is a spot where, because of how it's moving around and the gravity of the sun and the Earth together, it's a stable spot. It's a very simple physics idea, but it's going to sit way, way out there, which means if it breaks, we can't do anything about it. It's too far away. When Hubble had some issues, we could send space shuttles and space programs to it. But when you're 1,000,000 miles away, well beyond the orbit of the moon, it has to work, which is why it's being thoroughly, thoroughly tested, including this is the sun shield. The sun shield is being tested north of Grumman right now, just outside of LAX. And the sun shield is essentially a giant parasol, a giant umbrella on the beach to prevent the telescope from getting very, very hot. The telescope operates in a wavelength range called the infrared, which is longer wavelengths than our eyes could see. This telescope is going to operate entirely in wavelengths of light we cannot see with our eyes. And as a result, it needs to be very cool. Because I'm right now, you as well, we all glow in the infrared just by virtue of the fact that we're warm. Our bodies are warm and we are warm-blooded. And when we're warm, we glow in the infrared. That's how infrared goggles work, night vision. And the telescope cannot be warm as a result, because if the telescope is warm, it's glowing in the same wavelength as trying to take a picture. It's like trying to take a picture with a camera that's on fire. You would not want that. It'd be too bright. So you want the telescope to be very cold. And as you can see, it's 185 degrees Fahrenheit on one side, which is hot, even for Tucson, and negative 388 degrees Fahrenheit, which I call my time in Hanover, New Hampshire. I'm from Southern California, so I'm from, I guess, right in the middle perfectly all the time. This is what the mirror looks like. This is probably one of my favorite pictures in this whole talk. This mirror was built and assembled at at Goddard Space Flight Labs in Baltimore, Maryland, in this enormous clean room. There's some windows over here that are the visitor gallery windows. And I was working from a room over on this side with my my colleagues at the University of Arizona, just a couple feet away, while this was being assembled. Each one of these mirror segments is about 50, 60 pounds. It's like this big. It's gold-plated because gold reflects infrared light. It was assembled painstakingly, one mirror segment at a time, and like put together, and then they lifted it up and then hung it upside down terrifyingly just to make sure everything was working all right. It was all, like perfectly polished and perfectly smooth. Then they packaged it all up and they stuck the instruments on the back of it, and they shipped it off to Houston. Actually, I'll talk about the instruments. Here are the instruments. Let me talk about the instruments for a second because this is why I'm here. So when you have a big telescope, you need cameras on it. And there are 4 cameras, essentially, that are attached to the telescope. The light from the mirrors gets bounced and focused onto these cameras. Like, these are very fancy cameras. This camera up here is my favorite one. This is NIRCam. I'll show a better picture of this in a second. This is NIRSpec. So NIRCam is a University of Arizona instrument. The primary investigator is one of my personal heroes, Dr. Marcia Ricci. She was the person whose door I knocked on. She worked on Hubble, on one of its main instruments. She has an enormous amount of history working on space telescopes, which is a crazy thing to say, an enormous amount of history working on space telescopes. She's incredible. Her office is just up at Steward Observatory. She's one of the most warm, wonderful people, and she's the primary investigator on this. So she is my boss, and she's the one who, for 20, 30 years, has put together this instrument and tested it and knows more about it than anyone. She's like a national treasure. And this right here is NIRSpec. So this is an American instrument. It's the University of Arizona's, and it's the main camera. Meaning, when you see images, those beautiful images, when they make inevitable IMAX movies based on James Webb images, the camera will be a University of Arizona camera. So, hey, hometown pride. Yeah, it's pretty cool, right? It's very cool. And then this is NIRSpec. NIRSpec is a European instrument. It's the Spectrograph. It's like a fancy prism. So instead of taking images, it spreads the light out over its component wavelengths and looks at that. It's a European telescope. The primary investigator is at European Space Agency and is a French gentleman who we work very closely because these are the 2 main instruments. This is MIRI up in the top right corner. My laser is freaking out right now. The MIRI up in the top right corner, and MIRI is a European and American joint instrument, and it's a longer wavelength instrument. One of the American scientists is Marcia's husband, George Ricci, who's also a national treasure, and his office is just up the way. George and Marcia Ricci have worked together. George also worked on another space telescope instrument called MIPS. And then down here is NIRISS, which is the Canadian Space Agency instrument, and it's kind of like a prism, but also like a camera. So these all 4 will work in concert with each other to essentially look at the universe. And I'll talk about why that's going to be exciting for the rest of the talk. This is NIRCam, zoomed in. I want you to notice, eagle-eyed viewers will notice that it looks like there's this black plastic thing, and then it looks like what's on the top is mirrored on the bottom. Can you guys see that? That's because NIRCam is really fancy in that when they built it, they built the 2 of the exact same instruments sandwiched on each other. So when you get an image, you don't just get one image. It's like having 2 cameras right next to each other. You get a big rectangular image. So you can see here, this is what one image will look like. It will have this region here and the region next door. But even cooler is that inside of NIRCam is like a special piece of glass that separates light at 2 different wavelengths. We call it a dichroic because it splits light based on its color into the short wavelength color and the long wavelength color. So when you get an image, you get 2 images of the same field and then 2 images of the other field at different wavelengths, which is great if you want to use your time wisely. And NIRCam, compared with Hubble's main imagers, they're like a little bit smaller than the size of one of these regions here. So it's very, very exciting. We have a whole bunch of cool stuff planned for it. So I'm pretty jazzed about this. This is when they took it and stuck it inside of a big chamber in Houston to do some testing. They bounced light off the mirrors to make sure the mirrors could wiggle independently, each individual mirror segment. I'm pretty excited about this. It launches in 2020 on an Ariane 5 rocket from French Guiana. It's a world collaboration. I'm very proud to be a part of this collaboration. There's a lot of great scientists just up north who are planning some of the early science that's going to be done with James Webb. And it is an expensive thing now. It's like $8 billion. And Hubble is, similarly very, very expensive. It's a huge project that NASA has undertaken. And the question then is, why do we do this? Why do we build these telescopes? And now for some of you in the audience, you are like, you don't need to ask that question. Of course we should build telescopes. It's just, it's the progress of science. But I think that this question is, I'm thinking about it in a bigger sense. Not just like, why do we invest in science? But more like, why as humans do we build telescopes? And when I say telescopes, I mean something broader. Humans, astronomy is perhaps the oldest science. There may be some scientists in this who might argue with that. But I think that astronomy and the idea of looking up and wondering about the night sky is as old as humanity. And we know this because some of the earliest scientific sites in the world are astronomy sites. This is Nabta Playa. It's in Egypt. This is Egypt's Stonehenge is a recreation. But essentially, these stones are oriented in a way where they are oriented with conjunction to various important celestial events. Sun rising, star rising. Because astronomy is the foundation of both space and time. Astronomy gives us our time. The motions of the sun, the rhythms of the sky at night, and the motions of the sun. That astronomy right there, that is the foundation of linear time for humans. It gives us a change. There's a daytime and a nighttime. The daytime gives us bright sunlight and warmth. The nighttime gives us this incredible splendor of the sky. Things change over the seasons that tie into when we should plant and when the Nile might flood. And these are the things that touch and are fundamental inside of our DNA, like this idea that the sun rises and sets and gives life to plants, right? And we built these instruments to try to track them and understand them. Not the only one, obviously, the actual Stonehenge in Britain. So this is like, from probably like 5,000 years before the Common Era, right? And this is, like a couple thousand years before the Common Era, right? This was a similar thing, that there were important times in the year when the sun was at a very important position, and they thought, gosh, it keeps coming back to that. Let's mark that. Let's celebrate that, because that has incredible ramifications for our entire lives and the agrarian society that we live in. In the Yucatan Peninsula, the Mayans built this entire temple, 1,000 years ago, to Venus, just the motions of one planet. This is El Caracal at Chichen Itza. It's a temple to Venus. The windows up there point towards important spots where Venus is. And we've found Mayan codices, before they were burned by the Spanish coming in, we found these existing Mayan codices that are just big tables of when Venus rose and set. Because we cared about this. We cared about this so much. This was the foundation of the big questions, the fundamental source of these big questions. What are we doing here? What's going on? Well, we have these patterns, and these patterns are outside of human existence, and we can write them down and try to analyze them and try to put significance to them, both religious and personal. Here's, in Wyoming, Medicine Wheel, which is the Native Americans doing a very similar thing. Horizon astronomy. These lines line up, and the rocks line up with important rising and setting, right? So we're all grappling with this. And so the reason we build telescopes is this is big question. This big question that we've grappled with. And astronomy is like the latest way to look at that. The big question is, why are you here? This is the big question. Not just like, why did you come to this lecture series? Because I had to, because it was interesting, because I love 9:30 talks. But the bigger version of this is the version that I think astronomy you have to grapple with. When I give talks like this to actual astronomers, they roll their eyes because they're like, don't ask people this question. That's not why we're here. We're here because we want to understand exactly the interstellar medium's relationship to stellar birth. No. I want to think about this question because I think that you do yourself a disservice if you approach science without thinking about a bigger picture question of the point of this. And I think that for astronomy, why are you here is the big question to ask. Because all that we're trying to do is figure that out, I think, as people. Why are we here? What's going on? What's our purpose? And to do that, I want to share with you guys a story that starts 13.7 billion years ago. And you are a part of it, so watch out. So 13.7 billion years ago, this is a big thing I'm about to do. The universe began. And it began in this incredible explosion of light that we call the Big Bang. And the Big Bang was a profound explosion of light and energy. And that was it. It was just light and energy streaming through the universe. And you were there. You don't believe it. But the stuff that makes you up, you feel like, oh, I'm 20 years old, I'm 15 years old, I'm 30 years old, I'm 50 years old, I'm only that old. But no, the stuff that you're made of and the energy that you use that propels you, that allows you to breathe, was there in that miasma, in that Big Bang. It was there. You were there, just spread out and different. And over thousands of years, millions of years, you cooled down, the energy of the universe cooled down. And for a long time, the universe was just light, and then that light was turned into very simple gases, hydrogen and helium. Again, you were there, just very simple. And for a long time, the universe was dark. We call this the Dark Ages because it was a period of time when stars had not been born yet. And slowly, the gas clouds collapsed and coalesced, and they heated up. And they moved faster, and they started giving off a little bit of light. And in the very dense cores of these gas clouds, these pristine gas collapsed down and started to fuse. This process of taking the simple gas and pushing it together and releasing an enormous amount of light. And so you're seeing here a simulation, because the thing is that we don't exactly know how this process happened. We have to simulate it because it's very hard to observe. In fact, you might need a giant telescope that would barely fit in this room to analyze that. And that's one of the reasons why James Webb was designed. It was designed to probe this early process, the opening up of the universe, the end of the Dark Ages, when the universe experienced this renaissance of things happening that had never happened before in the universe. Baby stars being born for the first time. And they don't live very long because they're enormous, these first stars we think. And they explode. And that gas goes into forming new baby stars, and those explode. You can see this here in the simulation. A star has exploded and is releasing this shell of light that's passing and lighting up the universe. But this process, which we call reionization, is fundamentally important for you. If this didn't happen, you wouldn't be here. If this didn't happen, humanity would be a lot more boring. Because this right here, the early stars, were doing something that has ramifications and that we need to study as astronomers, and that there are many astronomers trying to study, and James Webb is uniquely positioned to try to study because of its wavelength range and the size of its mirror. Because inside of those stars, the thing that is happening is that stars are taking this simple hydrogen and they're turning it into more complicated stuff. They're taking hydrogen and going, hey, now it's helium. Oh, cool. Oh, look, helium. Now it's carbon. This cannot happen anywhere else right now, because fusion is very, very, very difficult to do, requires incredible pressures and energies that only the core of a star can fuel. And so we look at this process and we start to see this go together as hydrogen and helium and more of these atoms start to being pushed together. And what goes on is as these stars start to push together these atoms, those atoms get eventually spat out into the universe to form new generations of stars. And so you're seeing here that at the cores of some of these stars you hit iron, which means that the star cannot support itself, and the star will eventually explode in a supernova, an enormous explosion that is great for us because it means that all of the gas and stuff that was made in that star is suddenly pushed outward into the universe. And why is that important? Well, because you guys are made out of carbon. And where did that carbon come from? A star had to die so you could be put together. That is a thing I like to tell people that they do not believe. Your fingers are made of stuff that was put together inside of a star initially. The reason that you are here right now is because stars lived their lives and died before you were born to put the atoms together. It gets crazier. I'm wearing a ring that's made out of silver. Maybe you're wearing some gold. Heavy elements don't just get made in dying stars. They get made when you have two stars that are dead. We just learned this last year. Two stars that are dead. We learned this last year, and I haven't updated my video to show this. Two stars that are dead coalescing in some sort of crazy, terrible death tango to explode, and in that process, energetically, all of the heaviest elements are created. Gold was created when two stars had previously died and then crashed into each other. This is mind-blowing because it is a thing that makes you realize that you are not just like this old in the history of the universe. You are actually part of a series of things that stretch all the way back to when you were light energy floating around through the cosmos. And the way that I like to think about it is that A long time ago, if you could put little tracers on all of your atoms in the universe, then for like one brief second, those atoms were in stars and they were out, and then for just a tiny bit, they're you. And then after you're gone, they'll be spread out in the universe again. So you are a collection of 7 billion atoms that were created inside of stars as those stars lived and then died and then collected slowly to make what we know around us. And what's cool about this is that the way we know this is from observations. And the way that we're going to learn this better is through James Webb. James Webb is designed in the infrared to look at galaxies that are farther than any galaxies we've ever seen. It will make Hubble look it's looking at the foreground. James Webb, and the work that I do just up north of here is trying to look at the light from one of these little fuzzy blobs and figure out exactly how far away it is, which means I can tell you how far away we're going to see things. And it's almost peering all the way back to those first stars and that first end of the Dark Ages gas. And over time, and over James Webb's lifetime, we will slowly and actually probably hint at getting at those stars. And why is that important? Because that gives us a chance to look at the evolution of heavy elements in the universe, to look at how the universe went from light to putting you together. Just this beautiful record as we slowly march forward, because we can look at these, because astronomers are very smart. We can look at these fuzzy blobs and tell you how many stars are being born every year. What's the chemical makeup of those elements in the gas there? Like, how big is it? Is it a spiral? Like, we can tell a huge amount from this. It's harder with the really little fuzzy, far away ones. Mostly, we're just hoping to find those. That's the first step. But for a lot of the stuff, we're going to be able to really get in and understand exactly what's going on, and therefore make a timeline of just the history of the universe's heavy elements, which is pretty profoundly important. And so, this is the image that I want to start with. This is why we build these telescopes. This is an image of Congress Street here in Tucson back in like 1920. And what's cool is if I handed this to you, you're probably looking around and going like, do I recognize that as Congress Street? What's going on? I think that this is looking towards a mountain down the street right there, right? So this is looking towards the west. And I think that what you do is what I do when you look at an image like this, which you kind of like zoom in on a lot of stuff and go like, oh man, there's like a shoe store on the street here. I can zoom in on that thing there. Or like, oh, look what this kid's wearing. Like he's got like a fun neckerchief and like this little cap on his bike, right? But you're limited, with an image like this, you're limited to the resolution of the image, right? Like it's hard to see. I zoomed this in. It's hard to see. Is that like a little red cross? What's going on that, right? And astronomy is the same way. But astronomy is kind of cool. This image is one of the images that we have in the the Arizona Museum of University of Arizona Museum to show historically what old Tucson looked like. But we're limited to whoever decided to stand out in the middle of the street and take a picture, right? By that. But astronomy is cool because our telescopes can take images of the past and take better and better images of the past as we get better cameras, right? So when we say a telescope is a time machine, it's literally like looking back. But instead of looking at all these people and looking at the zoom in, we now can make better and better telescopes to look at the same thing. This is an image of Congress Street billions of years ago. This is an image of galaxies stretching back. This is that same image I just zoomed through, but a much higher resolution. Every dot in this, except for the ones with the spikes here and here, there might be other ones, but everything here that doesn't have spikes is a galaxy. Every one of these. So this little thing right there, it's a galaxy. It's a galaxy. It's a galaxy. It's a galaxy. Galaxies have about 100 billion stars. We live in one called the Milky Way. So you're looking at untold numbers of stars, stellar systems, potentially planets. And you're looking at an image that stretches back as far as we've ever seen. So this is like looking at not just a baby picture, but it's like looking at one of those like family reunion pictures where you see all the generations together. That is what you're seeing here. And James Webb will take an image of this that will just blow this out of the water. Not just from the fact that it's going to see far the little smudgers, but also like here's a zoom in on one of these galaxies where you can see that it's kind of like, okay, it's blue and white. It's this one right here. What's going on? But James Webb, they ran a simulation. James Webb will allow the resolution of individual groups of star forming. And also you can see that there's entire other galaxies that you wouldn't be able to see to begin with out there. James Webb is going to revolutionize the field of galaxy evolution. It's going to do that thing I just described and understand it not just in a hand-wavy detail, but like really do that. That was why it was one of the main reasons why it was built. And it's very exciting. It's very, very exciting. Because galaxies are incredibly diverse. And the question of why they're this diverse is like one of the foundational questions in my field, right? And the reason that we care about this, and the reason why this is important, is because this is like the diversity is something that we get excited about. When astronomers and when scientists see that there's a type of object that is incredibly diverse, we get very excited. Diversity is very cool for astronomy because it is a thing where we can go, why? Why? What's going on there? Why? Like, you're probably looking at this and already picking out things that astronomers pick out. Like, some of these are blue, some of them are red, yes, yellow, red, right? Some of them are really pretty spirals. Some of them are, I guess, blobs, right? Like, these are, like, some of them have these things in front of them, right? Like, this is what astronomers like look at and get excited about, and James Webb will be able to have the resolution to trace the evolution, to trace the evolution of properties, these morphological properties, why they look like this, which is really very, very exciting, right? And for close by galaxies, we can like use the telescope to look actually at them in a way we haven't before. This is a Hubble image of the Whirlpool galaxy, but notice there's a bunch of this kind of red spirally stuff that's in the middle of the arms. That's dust. It's kind of like soot. And James Webb operates in the infrared, which means we can like peer right through that soot, because infrared light will pass through a lot of that dust, and we can peer past the dust. Dust is a pain in the butt for astronomers because it blocks what we want to see. But if we have the ability to peer through it, we can start to see how stars are being born and see individual groups of stars in distant galaxies, which has never before been done with this resolution. And so when you start to do that, you can take these images like I showed you at Hubble image here and peer inside of those little dusty cores here. Here's a zoom in of a star-forming region, and then the same region in the infrared down here. And you can see, what's going on up there? I don't know. There's a group of baby stars in there. Why? Why do we care about that? Well, I'm not done with our journey yet. The reason we care about the birth of baby stars is because, and let's flash back about 5 billion years ago, we're in a young version of the Milky Way. And in this young version of the Milky Way, there is a big gas cloud. And you were there. Again, not put together. And slowly, the gas cloud collapsed, and that gas cloud has dust which blocked the way like a little cocoon, and those little cores collapsed, and eventually one of those got hot enough in the very center that it started to fuse, and it turned on. And around that, there's this enormous amount of like little rocks that like are left over from this process, and those little rocks are coalescing as well. Those little rocks are collapsing to form a group of little planets around this star. And these planets are young, and they're vastly different sizes, and they are, and some of them are very hot. Like one of them, about a third out, is very hot, and over time, little rocks from space keep crashing into it and delivering water on there, and you're starting to build this, and it's violent. It's a very violent period of time, because all little rocks are still spreading out through this little nascent system, and the little rocks are crashing into all of the other planets. And so we're getting this one rock, which we'll call Earth, I guess, is getting bombarded with little rocks from space. It's bringing water, but it's also, at one point, something crashes into the Earth and knocks a chunk off, which starts to orbit around us. And thank goodness this thing happens. Thank goodness this thing creates a moon, because a moon delivers us the tides. And the tides are really amazing for the young life that is starting to develop on this little blue ball. This moon is mixing the tides up, which might have an evolutionary help to like mix up and diversify. And so the thing is that starting from the Big Bang, the universe took light and then slowly created life. From light to life. That's what the universe did for you to be here. And you have to value that. That's an amazing miracle that has happened, right? And the big question, like, and so the life that stepped forward onto this, like, was underneath a sky that was filled with evidence of this possibly happening other places. The night sky is a reckoning with what has happened, right? You see our own galaxy stretched out. In our galaxy, you see groups of star-forming regions. You can actually see a star-forming region with your naked eye in Orion on a dark night. You can see these star-forming groups. You can see other stars. It is a reckoning that it is a thing like you can believe, as many people did, that we're at the very center of things. But the night sky is a reminder that we are not. And I think that that's a terrifying thing for a lot of people. We build, like in the last 100 years, the Industrial Revolution has brought electrical streetlights and all sorts of lights. And so now we literally live in a world where we spend a lot of our times trying to ignore the fact that the sky is beautiful and above us, especially at night, by turning a light on our face and pointing it directly at our face at all times. I know this. I've lived on a college campus for many years. College students really get excited about cell phone light in their face. And like this is a thing that like we, up until a couple hundred years ago, this was every night. We lived in a world where this was the reckoning we had to make every single night. And why is that also important? Because we're not the only solar system out there. We're actually finding evidence that there are solar systems around pretty much every star. It's hard to find these though, because stars are very bright. Very, very bright. And you have to find these tiny things that don't glow on their own, that are just orbiting it barely. Studying planets is a very cool thing. A lot of astronomers do. Some of my colleagues down the hall are planet people. And they are very excited about this because we're just now entering a time where it's not just like collecting, systems, but understanding what's going on there is fundamental. Right? And so this is the big question that we as scientists and as human beings are going to have to reckon with in the next 20 years, which is this idea that okay, we've looked out at the night sky, we've wondered where we are, we can trace the history of our being put here, but has this happened anywhere else? I think the biggest discovery in all of science, and this is very, very self-centered, but I think the biggest discovery in all of science is going to be an astronomy discovery of the existence of life outside of our planet. The fact that we did not walk this journey from the beginning to here alone. And we're just now entering, because it's very, very hard to look at planets. And so James Webb is designed in part to look at the atmospheres of planets in a very clever way. Sometimes planets will orbit right in front of their host stars. And in that tiny bit of time, light can pass just grazing through that tiny onion skin of an atmosphere. Just barely through that. And we can see what light gets scattered out from that and look at what's left over light through the atmosphere and tell you a little about what's going on in the atmosphere. That is something that's being done by my colleagues, and it is very difficult. I do not do this because it is very, very difficult to do. I work on galaxies because relatively it's a little easier than trying to suss out the goings-on of an atmosphere of a planet that is, incredibly distant, right? And what we're hoping to find is evidence that atmosphere has things in it that may be evidence that something's going on there besides just, it's like a big Jupiter. There's nothing really. We don't see any life. It's a big gas giant. Instead, it'd be great if we could look at planet atmospheres and say, oxygen, ozone, methane. Maybe there's cows burping on that planet as well, right? This is the thing about atmosphere science, is that our atmosphere tells a lot about what is using the atmosphere, right? And another very cool thing that James Webb will be able to do is that James Webb will be actually able to take images, direct images of those planets, which is so hard. It's like if I took one of those big spotlights they use to advertise car sales and just pointed it all over your face right now, and you're like, oh, this is too bright. But then I put a little firefly on the edge. Can you see the firefly? No, you can't see the firefly. There's a giant bright light in your face, right? You can see just how bright this star is, and we've blocked, this is an example of simulation, we've blocked a lot of the light from the star with this occulter, and yet even then you have to do some very clever spinning and twisting to slowly get at the planet. Direct images of planets outside of our solar system. This is a revolution because this allows us to see these planets that are growing and to see how they shape the young solar system that they're growing into and how the young solar system shapes them. Because we are always asking ourselves, why are we here? And astronomy gives us a chance to see that happening, see the processes happening that put us here in the universe, mirrored back at us. We have a time machine. We have a time machine, and we have an ability to look at the universe around us and actually piece together all of the parts that put us together. And that is one of the unique joys of being an astronomer, is that I get an opportunity to, instead of wondering, when I was a kid, I could either study dinosaurs or space. Those are the only two things I could ever imagine myself studying. And I at one point said, I'll never see a dinosaur in my life, but I will see a galaxy, and I will find a black hole. And I will find pictures of them, and I have, and it's been great. I love paleontology, it's this very cool science, but I wanted to be able to see the things that were the answers to my questions. And astronomy gives us this. So I'm gonna finish up with the kind of roundabout thing, which is, and humanities-wise, the kind of reason why. First off, there's this quote that I like from John Muir, who says that when we contemplate the whole globe as one giant great dewdrop, striped and dotted with continents and islands, flying through space with other stars, all singing and shining together as one, this is the important part here, the whole universe appears as an infinite storm of beauty. And I really like the words there, infinite storm of beauty, because he uses the word storm to describe this. He's looking, this is from his travel logs when he's going up to Alaska, and he's looking at clouds, so he's in a very stormy mind. But he refers to the universe as an infinite storm of beauty, because we sometimes think of storms as dangerous, and they can be, but storms are creative forces, right? That's the reason we call a brainstorm. It's a creative force, and the universe was a creative force that put together so much beauty. The universe as infinite storm of beauty. I really like that. Thanks, John. But I think that when people often talk about astronomy, and when you go see astronomy videos and movies and stuff, like or go to IMAX, you'll hear like some big booming voice, you know, the universe is vast and you are tiny compared. And I hate that. I hate that because that otherizes science. Like 14 billion. Like it makes you feel like insignificant. And people tell me, they ask me, they go, Kevin, how do you do it? Sometimes I look out at night and I feel so small and so nothing. And I think that is my central charge as a scientist, is that you should stop otherizing science and start internalizing science, because you should look at science as from the point of view of a human, not from the point of view of some cold robot who's trying to not use their emotions and understand the beauty of the universe and understand the beauty of the thing that you do. Because if you do that, you will remember that 14 billion years ago, the universe put you together from light itself in varied and interesting ways. It put people together in strange, interesting ways, and all of them were set under the same sky, looking up at the same stars. Some of the stories were shared over time. We can look at certain groups and patterns of stars and recognize that one culture that never talked to another culture looked at it and saw the same thing. And this all is profoundly connecting you. The stars connect us. They do not dwarf us. They are a thing that exists, and we exist alongside of it because of the actions of these stars. You are this assemblage of 7 billion atoms flying through the universe on this crazy spaceship that is one of the only places where we see liquid water, which is good because it's good to drink. And we are the beneficiaries of an incredible amount of things that have happened to put us here. So I'm going to finish with that idea that you should not feel small by the universe, but you should instead look at the universe the way that you look at any art, as an understanding and as an example of the human experience reflected back. The universe put you together, and you need to put the universe together inside of your brain, because it is the most incredible thing to have put you together, to be here. Okay? So if you have any questions, my name is Dr. Kevin Hainline, and I'd love to answer them right now. Thank you. All right. Questions? So I see one in the back over here. This is my favorite part, when a microphone is shuttled around. There's a microphone that people have that's like in a big fuzzy thing that they throw around a room, which is really very exciting. Yes?
Yeah, I'd first just like to compliment you on a talk that was maximum in its clarity.
Oh, thank you.
And in its enthusiasm.
Thank you. I appreciate that. Thank you.
I have a question about the title.
Yes.
Why are we here? And when I saw that, I thought, wait a second, does this go to purpose? And then you explained it as a concatenation of events over billions of years. But you concluded that with the question, what is our purpose? So that's a humanities question.
Yeah.
I'm asking you, what is our purpose?
Okay. I'm going to talk about this from the point of view of a scientist, in case there's any of my colleagues in the room who are going to roll their eyes. That is partially a religious question, and I don't know if I have it within me to answer that from the point of view of a scientist. But from the point of view of a human being, over here, scientists stay over there, the point of view of a human being, I think that when you are the beneficiary of events that have happened, I think that the only purpose that you must have inside of you is to relish that and find joy in that and use that as to love. I think that like this is very touchy-feely, and astronomers really hate when I get to this touchy-feely, but I think that like our primary purpose as human beings is to love and to like hold on to the fact that we are all this crazy assemblage on this thing, and not use that to like gain power over other. Like that's like a silly thing. Like if things happen to put you together and you're a delicate miracle, why would you do anything else but celebrate the delicate miracles that are around you? And so I think that that's the primary purpose. Now, scientifically, that gets into religion and a bunch of stuff that I don't have any purpose over, and maybe there's some theologian in the room who like has a better explanation. But like that is the big thing that humans have grappled with, is what it really is our purpose. And I think that like when you're so like incredibly like vastly complicated and from nothing, you have to share that and be enthusiastic about that and like hold on to that by loving as hard as you can. So hopefully that's the touchy-feely answer to your question. Yes, in the blue behind. And then I think there's a question down here. I guess it's teal.
Yes, thank you. Thank you for what you've told us so far. Einstein.
Yes.
Imagination is more important than knowledge.
I think that that's what separates us as a creature.
I'm aware that Kepler and Einstein and Newton had spiritual lives that were very, very important to their work. And Einstein made that very clear by the way he lived in the last half of his life, especially. I'm asking you in the imagination department to share with us some of your ruminations about the statistics and probability of the way that this kind of a situation here is distributed in the universe.
So,
and you know, it's like starting with our own Milky Way and going out to what you have shown us here with some of these images. Thank you.
So the problem with statistics is that it's very cold, and it's also reliant on us having other examples. And this is the big problem with anyone trying to do statistics to look at the universe, is that we have one example of life. It's here on the Earth. And when you just have one example, you can't do statistics. You can do some, but they're a very small number, and they're mostly pulled out of nowhere. And so there are a lot of things that could have happened and didn't. And we exist, but we would not have existed if they did not go right. So there's this principle that says like, well, we feel special, but also we wouldn't be here to feel special if it didn't go our way. And so there's this survivorship bias. Statistically, a lot of things happened that are pretty profound to put us here, and I'm very happy about that. I don't know if I can give you numbers to say that. I want to go back though to your statement about imagination from Einstein. I think imagination is really very underrated as the thing that makes us human beings, like the thing that separates us from a lot of different creatures, is the fact that we have this imagination, born from many different possible reasons why we might have this, maybe just evolutionarily, like fight or flight, if we can imagine the possible scenarios, it might help us. But like the fact that we can imagine, like that's why we do a lot of the things we do. That's why we build telescopes, is because we can imagine the things we might see. And I'm very happy that you brought that up, because I think that the more that you exercise that imagination as a muscle and as a thing that you use, and the more that you don't shut yourself off to the fact that you are a creative being, human beings in this room, like, if you're not doing something that requires some imagination, because of many reasons we might shut that off. There's an embarrassment. We're like, I can't be imaginative. That's silly. Like, let me tell you, I am the silliest person you'll ever meet in your life. I am the most enthusiastic, imaginative. I try to be so much, and it has never steered me wrong. Do not worry about other people criticizing you for being imaginative, because it is the best muscle you can use, and it's something that will only make you happier. So thank you for bringing that up. I don't know if I can help you super much about the statistics part, because right now we just know one example, and it's a great one, But until, like, talk to me once James Webb has started discovering, once we've discovered that life may exist other places, because then we have a couple other examples, and then it's really, we're off to the races. I think there was a question down up front, yes. I think there were two, yeah.
So I was really curious about your experiences with the public versus your colleagues in your ideas and personal viewpoints on this.
I joke about this a little bit. I think that science is like thought of like you go to like a lot of school for science, and it like weeds out a lot of people, which is bad. It weeds them out for bad reasons because there's a very competitive aspect to science. And I think that science at its best is very collaborative. And I'm very lucky I work with a lot of collaborative people. But I have a different background to like why I do a lot of this outreach stuff, and I have a lot of experience doing it and speaking about these sorts of things, which means that I have been able to speak in contexts where I've not gotten pushback. But a lot of astronomers, most of their talking experience comes, and most of their outreach and sharing experience comes in a very formal, lecture-based or colloquium research experience thing. And so they just don't have an opportunity to go out and say something that's inside of their heart and say something that's more exciting and more enthusiastic and not like in a judgment-free zone. Like I'm very happy that I'm in front of a group of people who like are not gonna be sassy, but like there are astronomers who definitely like think that any amount of humor or any amount of like spirituality is taking steps too far. I'm very lucky because I think that we're entering in a time when astronomy, a lot of the young people coming to astronomy are coming from very diverse backgrounds and bringing their diverse points of view. And it's not nearly as diverse as it should be at all. And by the way, if any of you want to be astronomers, please do. We would love to have more young astronomers. But like these young astronomers are starting to bring more of the human element to astronomy. And I'm very, very blessed that like there are more astronomers who do art and who write poetry and who paint and who dance than there've ever been in the history of astronomy. And that's very, very exciting because it means that this thing where I get worried about what would my astronomer friends think if they saw my talk is going to be less and less of an issue. Yes. So, yes, I think that write down a couple.
My question was, so like multiple times you referred to the Webb telescope as like a time machine.
Yes.
And I was just curious, like how is it, like what makes it like a time machine?
So
How are you
here's
able
my
to do
example.
that?
Here's my example. Imagine that you live in the 1800s, and the only way that you get your mail is from New York, is that someone gets on a horse and rides that to you, right? So you tell your friend, hey, write me a letter. And your friend writes you a letter and then gives that to you, right? And it takes a while. So when you get that letter, you're not getting it from your friend as they just wrote it the other day.Maybe it's like I got a haircut today, and you get the letter, wow, they got a haircut. But you're not getting the information about what they got today. You're getting the information about what they got a week ago, right? Or maybe it's even longer. Maybe it's like a really slow Pony Express writer. Like a month ago, like maybe it's something where like you're getting news from the continent, right? Like from Britain. And like that news had to get on a ship and come across and then get on a horse and come across. And so you're getting this letter, right? So you're not actually getting information as it is right now. You're getting it as it was. You're getting information. And similarly, because light travels in a finite speed, the light that we see just in the stars has taken, you're seeing that light as it left 10, 15 years ago, 100 years ago, 1,000 years ago, which is really cool, by the way. Think about right now, there's light traveling through the universe, and in a couple nights, you will look up at it and see it. It's been traveling for 1,000 years. It's just 2 days away from seeing your eyes. That's like a pretty cool thing, right? But that means you're seeing those stars as they were 10 years ago, because that's 10-year-old light, 1,000 years ago. With James Webb, we're going to see light that's traveling through the universe for like 13.2 billion years, which means right now it's traveling through the universe. It's been traveling the universe through the entire history of the universe, this light. Traveling the universe, and we're just a couple years away from putting a telescope up in space that's going to finally capture that light. And when we see those things, we're not going to see them as the galaxies are right now. We're seeing them as it was when the light left the galaxy, just like you're hearing about your friend as she was when she wrote that letter. And so that is why when I show you that picture of Congress Boulevard, we can take a picture like that of distant galaxies and see them as they were. And if we want to find ones that are a little bit older, we look a little farther away where light's taking a little longer. So it's a time machine. It doesn't take us there, but it gives us pictures of that, which is very cool. Does that answer your question? Cool. All right, I don't know how many more questions I can answer. Someone should kick me off when I'm not, because otherwise I will just continue asking questions. So here in the white, I think.
First of all, thank you for the talk.
Of course.
And my question actually comes in response to your response to the first question, because you mentioned about religion. And
Yeah.
just as a disclaimer, not a theologian, but a religious studies scholar.
Cool.
So I was actually struck through the entire talk how some of the language that you use mirrored mythic language. So one that I noted down was, a star was born and died so that you can live, which already has this sort of teleological understanding. So, and then when we get to the end of the talk, you started talking about how the far-offness of science blocks something that's humanistic, and that we need to see it as part of us.
Yes.
And I actually was thinking about, at that point, some theories of how myth functions as a parallax, which, you know, borrowing again the same terms.
You're welcome.
But the far off and the nearby, and that's important for humanity to be able to reflect on the same question of why we are here. That we are here, but we recognize the far off, and moving back and forth between those 2 points of view makes us understand things differently. So my question for you then is, can you reflect a little bit on how sort of the idea of science actually fulfilling the same function as myth or mythic language?
Well, I mean, that like, what's great is that if you just trace it all the way back, like our understanding and reckoning with myths and story, like, branches off from astronomy, like at the very beginning of time, right? Like we had stories and shared stories about the things that were happening, and then applied those stories directly to the stars. Our star stories are, you know, the Big Dipper. The Big Dipper is actually the Great Bear. The Great Bear is, you know, seen by most cultures that we can trace back as a bear with hunters or a bear with cubs. There is myth right there, right? So astronomy is the story of myth become more cold and rational, right? Like it's as we realize, like, okay, well, the stars are not painted on crystal spheres. They're actually these far away things. And I am saying that scientists want to just like push that aside and say, like, okay, we can't. But you can't reckon with the universe without interpreting it through the stories that, like, you know, because, you know, like, the way that we can understand this is with the stories, like, this is a huge question that I don't know if I'm really properly ready to answer after a big talk, but like I think that like we have to, because it is like inside of us, like as storytelling creatures, and that we have to, because especially like just as specific, like all I do is write papers. That's what we do. Our language as academics is papers. And let me tell you, when you read a paper that is written by someone who's trying to write in a very cold, rational way, it's not nearly as exciting as when you read a paper by someone who understands the metaphor and understands the story they're weaving of the topic they're looking at. And I think that like you have to bring that in, just as an academic, I have to bring that in to be a more warm person. But also, just as a person to exist in the universe, to exist as a person, I have to reckon with, I have to think about the stories and the the way that I build stories in my brain with respect to the thing that I'm studying. This is rambling, I understand, I'm sorry. But I would love to talk with you afterwards a little bit more, because I don't have a lot of opportunities to talk with religious studies people, and I think there's a huge amount of that. I think that maybe I have to finish up. So thank you guys very much.